Right, what we're going to look at in this talk is calculating the equilibrium composition, and we're going to use a single gas phase reaction. And we're going to do it using an example. So let's take a simple case where we have A in the gas phase plus B in the gas phase reacting to form C in the gas phase. We calculated the equilibrium constant at the temperature of the reaction and say it's given a value of 2, and the reaction's happening at 2 atmospheres. Right, and what we'd like to know is what is the equilibrium composition. We also need to know what the feed flow rate is. And let's say the feed flow rate is not stoichiometric, and I've got 1 mole per hour of A flowing in, 2 moles per hour of B, and half a mole per hour of C. So I've actually even got some product flowing in. Right, if you're thinking of a picture of what this means, is we've got A, B, and C flowing into a reactor, and the reaction is going to completion, in other words, to equilibrium in this case. And equilibrium, so this stream is at equilibrium, and what we're wanting to know is what is the number of moles of A, B, and C leaving the reactor. Now the approach I'm going to use is to use the concept of an extent. Because there's a variety of ways you can handle this, but we need to know what the relationship is between A, B, and C if different amounts of materials react. So if I use extent, I can define that the number of moles of A is the feed flow rate, which is 1, and I say extent is the number of moles of A that react. B, then, the number of moles of B at any time is what we started off with, which is 2 moles per hour, minus how much reacts. And if an extent E moles of A react, then the same moles of B must react. The number of moles of C must be what we started off with, which is a half kilomole per hour. And if we used up extent E moles of A, then we must deform that many moles of C. I've specially set up the reaction that moles aren't conserved. We have 2 moles going to 1 mole, and therefore the total number of moles are going to change with reaction, and if we add those all up, we find it's 3.5 minus extent. Right, so the next thing we need to do is look at our equilibrium expression. Now the equilibrium expression, K equilibrium, is the partial pressure of the products, in other words C divided by the reference pressure, which is 1 atmosphere, and please, this formula is always in atmospheres. This pressure is in atmospheres, and that's in pressure is atmospheres, that's 1 atmosphere. So it's the partial pressure divided by the reference pressure of the products divided by the reactants, which is partial pressure of A divided by P naught, and partial pressure of B divided by P naught. And that we can then simplify, because the partial pressure is the mole fraction times the total pressure. So the mole fraction is the number of moles of C divided by the total number of moles of C. That would give us the mole fraction of C times the total pressure, and we've still got the P naught in there. So we do that for C, for A, and for B. And we can then simplify, because you see you've got some N totals above and below the line, and P over P naught's above and below the line. And if we simplify, we end up that we have number of moles of C times N total over number of moles of A, number of moles of B, and the ratio of the reference pressure, which is 1 atmosphere, to the reacting pressure, which we said was 2 atmospheres. Notice this is dimensionless because K equilibrium is dimensionless. We now have our expressions for NA, NB, NC, and N total, and we can take these and substitute into there. If we do that, what I get is that K equilibrium, and I've just taken the P over P naught over this side there, is as before this term, and I've now substituted NC. There's NC, and I've put it in there. N total, and I've put it in there. There you see it, divided by number of moles of A and number of moles of B. And now what I've got to do is solve that. I've rewritten the equation that we had on the previous slide over here, and what we're going to do is substitute the value of K equilibrium, which is 2, P is 2 atmospheres, and our reference pressure is 1 atmosphere. So I select that, or I substitute that, and I've also then multiplied to simplify this equation. I'm going to get a quadratic in the numerator and a quadratic in the denominator. So on this side, it's 2 times 2, which gives us 4, and it's dimensionless. If we multiply out, it's a half by 3.5, that's that term. Extent by 3.5, which is that term. A half by minus extent, which gives us that term. And extent times minus extent, which gives us minus extent squared. Let's do that in the denominator. Again, 1 times 2 is 2. Minus extent times 2 is minus 2 extent. 1 times minus extent gives us minus extent, and minus extent times minus extent gives us plus extent. I can simplify that by combining terms, and that will give me 4 is equal to, if I work that term out, it's 1,75. That term over there gives me 3 extent minus extent squared. The bottom is 2. Those two terms gives me minus 3 extent plus extent squared. How do I solve this now? Well, I've basically got a quadratic form here. I have to take this denominator, multiply it with the left-hand side, and then simplify. If I do that, what I get is multiplying the denominator with the left-hand side. I get 8 minus 12 extent plus 4 extent is equal to the numerator. I can combine terms, so I can combine the constant, which is 8 minus 1,75. I've taken them across effectively to this side. I combine like terms, so the 2 extent terms, minus 12. And if I take that across, it's minus 3, so that gives me minus 15 extent. And I combine the two squared terms, and that gives me a 4. And if I take the minus 1 across, it's a plus, so it's a 5. So I've rearranged them here in the more classical form. 5 extent minus 15 extent, 5 extent squared minus 15 extent plus 6,25 equals 0. Right. Remembering how to solve a quadratic equation, the extent then, remember that's what we're trying to work out. The classic formula is it's minus b, and b is the term in front of the linear term, so it's minus 15 plus minus the square root of b squared, that's 15 squared, minus 4a, that's a, times c, and that's the constant term, 6,25, divided by 2a, which is what we have over there. If I now take this further and have a look what it simplifies to, I get the extent is minus times minus, which is plus 15. This term is 100, so it's plus minus the square root of 10, divided by 10. And so I get an extent of, if I do the subtraction, it's 5 over 10, which is 0,5. Or if I do the sum, it's 2.5 of 25 over 10, which is 2.5. Now, which is the possible solution? With equilibrium, we should only have one solution, and let's have a look which one would work. If I go back to my definitions of how I calculated the relationship between moles and extent, Na is 1 minus extent. If I take a value of 2.5, I can see that I'm going to get a negative value of extent. And so what we can see is that that solution can't be possible. Extent has to be a half. I then substitute as 1 minus extent, get me a half. 2 minus a half gives me 1.5. And the number of moles of C is a half plus extent, which gives me 1. And so these values over here are the flow rates coming out the reactor. And remember, my units are moles per hour for all of them. So the concept is quite simple, but the maths when working out equilibrium can get messy fairly quickly.